Hi, this is lesson number 25, posted on June 3rd. This is really close to the end. So a reminder that quiz number 4 is on Monday, June 8th. We have homework due that night also. And then June 10th is our final from 2 to 4 p.m. I'll give you more information on this later in the week. Also, please complete your SOTIs. You should have been getting a bunch of emails about this. And then I'll also have an end of quarter survey. You can also see that there's going to be some extra office hours available, and also SI on June 8th to try to help you with all this. All right, so let's do a little bit of a review from last time. So last time we talked about titration, and when we're talking about titrations, we always have a base and we add acid, or an acid and we add base. So here's a point where we have a weak base and we add in acid. So that's why it starts off at high pH, right? This is basic conditions. And so we do this titration, we get this pH curve, and we're asked, what is the base concentration? So what I always say is, what do I know about my acid? What do I know about my base? Okay, so for my acid, that's the HCl, I have 0.2 molar. For my base, I know it's 50 mLs. And so, if I want to go ahead and look, I need to figure out this volume right here. This is the equivalence point. And if I look here, it looks like it's right around, let's say 22 mLs. Okay, that's of my acid. Now, you may say 25, you may say something else, but I'm going to say 22 mLs. All right, so that is my equivalence point. And at that equivalence point, the moles acid equals moles base. So I can use this information I know about the acid in order to figure out the moles acid. All right, so I go ahead, I take my molarity times the number of liters, and I get the moles acid. That'll equal the moles base at the equivalence point. Now remember, I also know there are 50 mLs of the base, so I can take that moles, divide by the number of liters, and I get the molarity. All right, so that is from last time on titration. Let's move on and let's talk about solubility. So we're going to talk about a special type of equilibrium, and that's solubility and precipitation. Okay, we dealt with this last quarter, or last in Chem 215, where precipitation is when we form a solid from a solution, right? We mix two solutions, and all of a sudden we form a solid, right? That's called precipitation. The opposite, a solid going into aqueous, that's what we call solubility. All right, so solubility is the ability of a compound to dissolve in a liquid. Typically, we talk about water. We can talk about other liquids, but in this class, we're going to talk about water. So let's say we have NaCl. NaCl is table salt. If I put that into water, what I'm going to get is I'm going to get aqueous Na plus and Cl minus aqueous. This is because salt, table salt, is soluble. We can also have things that are insoluble, like AgCl. And if I put solid into water, I get AgCl. All right, this is what we learned in Chem 215, and we actually had a table about this, right? Things were either soluble or insoluble. In reality, both of these things occur, and they're both equilibrium, okay? And so because of that, we have a K value for each of them, right? So for NaCl, it's Na plus plus Cl minus. And so what you can see is its K value, which is called KSP, we'll talk about that in a little bit, is 36. What that means is I have a lot more of my products than I have reactants. So we would call this soluble. For AgCl, it has a very small K, 1.77 times 10 to the minus 10. What that means is if I put AgCl, solid, into water, I'm going to get very small amounts of Ag plus and Cl minus. Okay? All right, so this is called KSP, or the solubility product of a solid. Notice when we're talking about solubility products, we never have a denominator, the bottom. And that's because this is a solid, so it doesn't go. And the larger this KSP, that means the more ions that are formed at equilibrium. Okay. All right, so let's say we have AgCl going to Ag plus and Cl minus. If we go in the forward direction, right, so here's my AgCl, and some of that dissolves, we call this dissolution, right? Dissolution is taking a solid and forming ions. The reverse of this, going from ions to solid, this is what we call precipitation, right? Forming a solid. Now, KSP, a few other things, it's dependent on the temperature. So as temperature increases, the K value increases. We know this because, if I make hot chocolate and it's that powder stuff, and I put it in cold water, it's not going to dissolve. But I put it in hot water, it'll dissolve, right? That means it's KSP, because it's just sugar, is increasing. It's forming more ions, all right? Now, KSP also depends on the ions involved, right? So notice if I have CaBr2, calcium bromide, it's going to form Ca2 plus and 2 Br minus. It doesn't stay as Br2. Instead, that 2 forms 2 bromide. We could also have something like CaBrCl. This would form Ca2 plus Br minus plus Cl minus. So the KSPs for these two will look something like this, where I put each of the ions raised to their power. Let's look at this bottom one. This is what we called sodium sulfate. Remember, sulfate was a polyatomic ion that we learned about in Chem 215. Okay? It has the formula of SO4 2 minus. So what's going to happen when sodium sulfate gets put into water? Well, it's going to dissolve, but that ion there, that polyatomic ion, stays together as SO4 2 minus. So I'll get 2Na plus SO4 2 minus. And so my KSP will be the concentration of the sodium squared times the concentration of my sulfate. All right. Now, because KSP and solubility is equilibrium, we can do a lot of the same problems we did when we were talking about other equilibrium reactions. So let's say we have this. We're told we put excess NaCl and we dissolve that into water. We want to know what the concentrations of Na plus and Cl minus are at equilibrium. All right, so I'm going to take NaCl, and it's going to go, it's solid, it's going to form Na plus Cl minus. These are aqueous. We have our K there, it's 36. All right, so we're just going to do an ice problem. So in this case, when we do this ice problem, what do we start with? We're told that it's pure water. And pure water is not going to have any sodium or chloride to start with. So these are going to be 0. So if these two are 0, and I calculate Q, it's also going to be 0. So if my Q is 0, my K is 36. What's going to happen? It's going to shift towards the right. Okay? So that means this is going to be plus X, plus X. I'm going to get X and X here. Okay? All right, now, what this means is if I want to now use my value for K, remember K is the concentration of Na plus, that's X, times the concentration of Cl minus, that's also X, and that equals 36. So X squared equals 36. X equals the square root of 36, or just 6. That means at equilibrium, we're going to end up with 6 molar Na plus and 6 molar Cl minus. All right. Here it is on the screen. We start off with an ice table. We plug in our change. We calculate X, and that's going to give us our equilibrium concentrations. Okay. All right. So notice we get 6 molar. What does this mean? Okay. Well, does this mean that if I have an entire pool worth of pure water and I put one tiny grain of sodium chloride in there, I'm going to get 6 molar sodium? No. This isn't just what I'm going to get. It's only if there's enough table salt, right? If I poured an entire mountain of sodium chloride in there, I will get 6 molar sodium, right? So this value for KSP, these equilibrium values, these are the maximum amount of sodium chloride that dissociates, right? If I put in enough, right? All right, so when we talked about solubility in Chem 215, we talked about solubility qualitatively, right? Whether a compound dissolves. No numbers involved. All we said was it dissolves, it doesn't dissolve. Now we're going to talk about it quantitatively, right? And that means we're just going to say the amount of a solid that can dissolve in a liquid. All right, and we're going to use something called molar solubility. Molar solubility is the moles of a solid that can dissolve in 1 liter of a liquid. So it'll be moles per liter. We can find molar solubility because this is the value for X in ice charts, right? So in that problem right behind me, it would be 6 molar, right, that we just did, or 6 moles per liter. We can also convert from molar solubility to mass solubility. So mass solubility is the grams of a solid that can dissolve in 1 liter of a liquid. This is very useful, right? And if I look up on Wikipedia or anything else, you can see this for sodium chloride, or if I type in table salt, I'm going to get all this information, including solubility in water, right? And notice I can put 359 grams into 1 liter, right? So if I have 1 liter, I could put in 359 grams of salt and it'll all dissolve. That's a lot of salt, okay? Notice I also have solubility in other liquids. We're not going to deal with that here, but we could look at different liquids. All right, so how do I go from molar solubility to mass solubility? All right, so let's look at this board again. So we found out X. X is going to be my molar solubility, okay? So if my molar solubility here is 6 moles per liter, and I want to know a mass solubility, well, I need to convert from moles to grams. How do I convert from moles to grams? That's right. Think back to 215, molar mass. So I can take 6 moles per liter, multiply this by the molar mass of NaCl, right? So that's going to, if I look at the periodic table, for sodium, it's 22.99. For chlorine, it's 35.453. I sum those up, and that's going to give me the grams per 1 mole, right? So that's going to be 58.453 0.443, right? And I do this, and I'm going to end up with my molar solubility, or my mass solubility of 351 grams per liter. Okay. All right, so molar solubility and mass solubility are good ways to define how much of a compound will dissolve in water. This is the maximum amount of grams that will dissolve. So let's say I were to put into 1 liter of water, I put 450 grams. Well, what's going to happen is it's not all going to dissolve. 351 grams of it will dissolve, and I can have left over about 99 grams that'll just be at the bottom of my cup, right? We see this all the time. If you put salt into water, it'll dissolve, but then eventually you see a mound at the bottom. That's because there's only a certain amount that can dissolve. All right, let's say I wanted to increase how much dissolves. What could I do? I could increase the temperature, right? If I increase the temperature, right, this 36 at 25 degrees C, it might be 45 at 30 degrees C, right? Which just means more of the sodium and the chloride are going to dissolve. All right, so that is looking at a KSP and a solubility product problem. Let's go ahead and have you guys do this one. This is video problem 25A. We're told we have CaBr2. CaBr2, when I dissolve it, I get Ca2 plus and 2Br minus. Okay, so this is my equation for KSP. Okay? So I'm going to go ahead and I'm going to ask, if I dissolve CaBr2 in water, what are the concentrations of my calcium and bromide going to be? What's the molar solubility? What's the mass solubility? And then how much can I go ahead and dissolve in 2.5 liters of water? How many grams can I do? All right, so I'll leave that to you guys. Okay, so in the last couple problems, we've been looking at dissolving things in pure water. And pure water meant, this is the problem we did a little bit earlier, that there were 0 molar Na plus at the beginning and 0 molar Cl minus. Well, what if there is already some sodium there? Okay, this is going to change my equilibrium. And this is something called the common ion effect. The common ion effect is the reduction in solubility of solid due to the presence of one of the ions. This is from a different soluble solid, right? So notice the presence of one of the ions. So these two solids have a common ion. Let's show an example, right? So if NaCl is dissolved in a solution of 0.1 molar NaBr, which is totally dissolved, what is the concentration of Na plus and Cl minus at equilibrium? Well, here's my equation, my reaction, NaCl goes to form Na plus plus Cl minus. But notice we've gone ahead and we've added in some Na. We have a common ion. So what's going to happen? If I increase the amount of sodium, according to Le Chatelier's principle, that's going to shift it towards the left, right? That means I'm going to get less of my ions forming, right? And so common ions decrease solubility. Okay? We could actually calculate this by looking at an ice table. Instead of starting off with 0, we may start off with 0.1, and we could see what this does, right? But for now, we're just going to say, hey, adding in a common ion decreases solubility, right? Okay, now let's go on, and let's just do one last aspect. And for this, we're going to bring in our old favorite, the reaction quotient, right? So we've said that K, Sp, is the solubility product. So for instance, AgCl, it would be 1.6 times 10 to the minus 10. This tells us the maximum amount of dissociation. Okay. Well, if I have a solution, I can have a Q value. And what I can do is I can compare Q to K, and that's going to allow me to determine whether I have precipitation or dissolution. Okay? All right, so let's explain this, right? So Q is going to be under any conditions not at equilibrium. So if Q was equal to K, that would be equilibrium, right? So let's say I had a solution here, and I had 1.3 times 10 to the minus 5 Ag plus, 1.3 times 10 to the minus 5 Cl minus. So when I fill these in and I find my answer, I get 1.6 times 10 to the minus 10. This means we're at equilibrium. And this is what we call a saturated solution, right? A saturated solution is when the concentrations are equal to the solubility. Okay? What this means is if I add in any more AgCl, it's just going to go to the bottom, right? So I might have some solid AgCl here, but I have a saturated solution. No more Ag and Cl can go into solution, right? Because I'm at the maximum. What if I have Q less than K, right? This is what we call an unsaturated solution. An unsaturated solution are when concentrations are lower than the solubility, okay? In this case, we can't have solid. The reason being is any solid that we put in there is just going to quickly dissolve because we want to increase from Q to K. And then we can have a case where Q is greater than K. These are very rare, and this is what we call supersaturated solution. A supersaturated solution is when our concentrations are above the solubility. Okay? So for instance, let's say I had a solution that had 1.6 times 10 to the minus 2 Ag plus, and 4.4 times 10 to the minus 2 Cl minus. When I go ahead and multiply these out, I would get 6.4 times 10 to the minus 4 for my Q. This Q is greater than my K. Remember we said at the beginning K was equal to 1.6 times 10 to the minus 10. So if Q is greater than K, what's going to happen is some of that Ag plus is going to precipitate out. Okay, that is what happens when we have a supersaturated solution. Right? Here is on the number line an example. So if Q equals K, that's saturated solution, no shift. So if Q is less than K, it's going to want to shift right. And it does this by having some of the AgCl dissolve. And if I have Q greater than K, in this case it shifts to the right or to the left, and this is through precipitation. All right, let's just show this another way, right? So in the middle is a saturated solution. It has the right amount of Ag plus and Cl minus such that Q equals K. On the left is unsaturated. We don't have enough Ag plus and Cl minus. And on the right, we have too much. Okay? So what's going to happen if I add more AgCl? What's going to happen to my unsaturated solution is all that AgCl is going to dissolve. Okay? And it's going to dissolve until Q equals K. Right? What happens if I have something that's saturated and I add in more AgCl? Well, that AgCl isn't going to dissolve. Okay? It's going to go all the way to the bottom and just stay as a solid. Okay? And let's say I have a supersaturated solution. What's going to happen is all that AgCl is gonna, or some of it, is gonna start precipitating to form a solid. Okay? This will occur spontaneously until Q is equal to K. Right? Here's just a visualization of this on a microscopic level. Right? So in an unsaturated solution, I have more of the solid going to aqueous, and I only have a very small amount going the other way. When I have saturated, I have equal amounts going into aqueous and into solid. And if I had supersaturated, all of a sudden my my solution would form a solid. Okay? Sometimes you actually have to add what you call a seed crystal. This is just some solid for all these things to bind to. Right? Okay, so let's do an example of this. Let's say we have this, AgCl, and we're told that KSP equals 1.6 times 10 to the minus 10, and we have a solution that has 3 times 10 to the negative 7th molar Ag plus and 2.5 times 10 to the minus 4 molar Cl minus. And we're asked, will it precipitate 4? All right, so we know KSP. What we need to do to figure out if a precipitate forms is we need to figure out Q. Right? So remember that Q is going to be Ag plus times Cl minus. I don't include AgCl. Why? Because it's a solid. Okay? All right, so in this case, I'm told that my Ag plus is 3 times 10 to the minus 7. My Cl minus is 2.5 times 10 to the minus 4. And if I go ahead and multiply these out, I get 7.5 times 10 to the minus 11. This is my value for Q. So what do I do? Which one is smaller? Q is smaller than K, right? So it's going to want to shift right, okay? If it has to shift towards the right, that means it has to have more of this form. So that means I'm not going to form precipitate, right? Because precipitation is when it shifts from aqueous to solid, okay? Let's look at this on the screen. I find my Q. I realize that my Q is less than K, so that means no precipitate forms. If my Q is greater than K, then I go ahead and I get a precipitate until Q is reduced to get me K. All right, so here is a problem you're going to do. This is for CaF2, calcium fluoride. We're told that it's slightly soluble. It has a KSP of 3.98 times 10 to the minus 11. So we're asked what the chemical reaction for this dissolution is, right? Remember, dissolution is just looking at dissolving, right? What happens if I have CaF2 and it dissolves? What is the mathematical equation for KSP? Then figure out the Q for a solution containing this much calcium and this much fluoride, and then will it precipitate form? All right, so that is it for lesson number 25. We talked about solubility, and solubility is the amount of solid that can dissolve in a liquid, in this case, generally water. We can find molar solubility. That's the X from an ice chart, okay? And then we can go ahead and we calculate the mass solubility based on this. For this, we're going to need to use the molar mass. All right, we talked about KSP, which is our solubility product. And we also talked about briefly about the common ion effect. That's reduction in solubility due to the presence of a common ion. It reduces solubility. We know this because of Le Chatelier's principle. We could actually figure this out with an ice chart, but we're not going to do it here. All right, there's one last thing the book has this, and I don't know how useful it is, but when we say molar solubility is X from an ice chart, well, the value for X is dependent on the charge of my cation, which is positive, and my anion, which is negative. So let's say I had something that was positive, like let's say Na plus and Cl minus. These would form something like NaCl, and my X would end up being the square root of my KSP. Right? We can find this from an ice table, and actually we did this problem and we got square root of KSP. If instead I had something that was too positive, like magnesium 2 plus, and something that was negative, let's say F minus, these would form magnesium F2, and we could do the ice table and we'd get the cube root of the K over 4. We would get the same thing if we had something that was a cation that was positive and an anion that was 2 minus. This would be, let's say, if I had O2 minus and Na plus. And let's say I had something that was 2 plus and 2 minus, right? Then I would get this value right here, right? All right. So we also talked about precipitation. In precipitation, we always look at Q versus K. If Q is less than K, then it's unsaturated. That means more will dissolve. If Q is greater than K, that means it's supersaturated, and that means we'll form a precipitate. And if Q is equal to K, that means we have a saturated solution. All right, there's one other thing that they talk about in the book, and that's something called selective precipitation. We're not going to talk about that here, but what happens if I have a bunch of different ions and I can form more than one precipitate? The one that usually precipitates first is the one with the lowest solubility, right? Because it's the one that really wants to form a solid the most. All right, so with that, let's go ahead and close it off. Remember that the homework for this is due on Monday, June 8th. Right? On that same day, we have a quiz, and then our final is on Wednesday. Take advantage of the office hours. Take advantage of the SI. Take advantage of, just emailing me and asking a question. All right? With that, bye.